Hi everyone, welcome to part 4 of lecture 8, and this is the last part of this lecture. In this lecture, we will see some beautiful intuition, or in other words, some useful relationship between the distributions, okay? But to going into the details of that relationship, let's start with an example. Let's start with an example. Consider a Poisson process with mean lambda per unit time, and what is the distribution of the first occurrence time? Let's start. Okay, let's remember some useful approximation we just seen in, if I'm not wrong, in lecture 5. So let's say we have some time interval, okay? We have time interval between 0 and let's say 1. And let's say this time interval is related with the arriving of the customers to the store, okay? Arriving of customers to the store. What that means, a customer can arrive to the store any time point of this interval. And to make it easy, we just divide this time interval into, let's say, 5 time buckets, okay? So each of them are time buckets. Then by using binomial distribution, because all these time buckets are Bernoulli trials, they are identical, independent from each other, or identical, independent and identical distributed. So if you remember, the binomial distribution can be considered as sum of the Bernoulli trials. That's why we can say that we can solve this kind of problem with the binomial distribution in the case of discrete. Well, in this case, we have divided this time interval into 5 time buckets. That's why we can say n is 5. And to solve this problem for a specific number of customers, let's say that is 1, okay? And the arriving of the customer can be thought as success and otherwise failure. That's why I can solve this problem as 5 to choose 1, and the probability of success to the 1 times probability of failures to the 5 minus 1, okay? And in general form, we can say that, which is n choose k, probability of success to the k, the number of successes, and probability of failures to the number of failures, n minus k. So this is the general form of the binomial distribution, right? So let's say, if you remember that, if we divide this time interval into much more time buckets, that will give us a better approximation. So if you don't remember those things, please revisit lecture 5, and you will remember that. If we approximate this one to the continuous case, that means we have infinite time buckets between infinite time buckets within this time interval, okay? Many of them. How can I approximate this one, this first one, to this one, the second one? Simply, the n will go to the infinite, right? Because n corresponds to number of time buckets. And in continuous case, we will have infinite time buckets. That's mean n in this formulation will go to the infinite. That's why I can approximate this general form of the binomial distribution by calculating the limit of them, right? So the limit of n choose k times p to the k times 1 minus p to the n minus k, and n goes to infinite. Well, let's do some magic here. Here, what is the expectation of the binomial distribution? Remember that that was n times p, right? N times p. And in the continuous case, we are given that the average customer will arrive to the store is lambda. Okay, we are given that information. That's why I can say that the n times p that corresponds to expectation. In other words, the average of successes in that time interval, which is equal to lambda, because that corresponds to average arrival. So the same thing, same manner. And in this case, when n goes to the infinite, the probability will go to the zero. That's why this n times p will be always lambda. Okay? And I can write, instead of p, I can write lambda divided by n. Okay? So let's rewrite this part, which is the limit of n goes to infinite, and choose k. And instead of p, I will just write lambda over n, which is the lambda over n to the k times 1 minus lambda over n to the n minus k. Okay, so that's mean if I calculate this one, this limit, I will find the corresponding version of this example for the continuous case, and that is called the Poisson distribution. Remember the solution of this limit, that is the e to the minus lambda times lambda to k divided by k factorial. Okay, so the lambda is the actual expectation or the mean of that distribution, and k is the number of arrival or number of success. So this is the PDF of Poisson distribution. So now let's say I have similar time interval. Okay, 1, and that is a one-time interval. And let's say I extend this one to 2 time interval. Okay, 2 time interval. In this case, I can approximate that binomial distribution into the Poisson distribution with 2. I mean, that is let's say this is a binomial distribution with the parameters n and p, and this one is this whole thing, which is the binomial distribution with 2n p. So I can approximate this part as the Poisson distribution with lambda. Okay, and I can approximate this whole things with the Poisson distribution with 2 lambda. Okay, if I extend this time interval into 2. Also, I can shrink or I can contract the time interval, like let's say this part. This is a binomial distribution with n divided by 2 p parameters. And I can approximate this binomial distribution to the Poisson distribution with lambda over 2. Okay. So for the conclusion, I can say that I can approximate the binomial distribution to the Poisson distribution based on the time interval. So in both cases, the p will be equal, will not change, it will be constant, and the lambda will be constant. Okay, don't forget that one. Well, if we generalize this approximation, we can simply say that what I mean. Let's say I just want to approximate this part to the Poisson, and let's say this is t. The length of that time interval is t. So this part has a binomial distribution with n divided by t and p. So that time interval has a binomial distribution with the parameters n over t and the probability, the p, the probability of success. How can I approximate this one, the Poisson? That will be the Poisson distribution t times lambda. So I can say that I can approximate any binomial distribution to the Poisson distribution based on the particular time interval, okay? And this time interval, the location of this time interval is not important. So regardless of the location of this time interval, I can just use the length of the interval. So this t, that part, can be here, or it can be here, it can be here, anything. So the important thing is the length of that time interval, because the approximation from binomial distribution to the Poisson distribution is based on only the time interval, the length of the time interval, okay? So please keep that in mind. And let's continue. And let's summarize first. We have the continuous case and a discrete case. For the total count, in continuous case, we can use the Poisson distribution. And for the discrete case, we will use the binomial distribution, okay? This is the first conclusion we just got. Okay, now we have the same time interval, okay? And we will focus on some other thing. Instead of total success events, let's say we will focus on the first success event, or in other words, first arrival. So, which is the x1, that is a random variable. And let's say we have some point here, and we know that the x1 occurred after point t. So I can write that one, the probability of x1 will be less than or equal to t is 0, right? Because I know that in this time interval, there is no success event, or there is no error event. That's why I can write the probability of x1 less than or equal to t is equal to 1, equal to 0. So I can rewrite this part as 1 minus the probability of x1 greater than t, right? I can rewrite this part. So remember the approximation we did here. We can approximate a time interval, a binomial distribution time interval, to the Poisson distribution. So this is our time interval, and the length is t. So I can approximate this binomial distribution to the Poisson distribution with the parameter t times lambda, right? Because I know this guy is actually the probability 1 minus the probability of the number of successes between 0 and 1 is equal to, so 0 and t is equal to 0. And I know that the location of that time interval is not important. The only thing we care about is the length of that time interval. That's why I can approximate this one to the Poisson distribution with the parameter lambda times t, right? So these guys, or this time interval, can be approximated to Poisson distribution, okay, with the parameter t times lambda, okay? So that is, this guy is associated with the Poisson with the parameters lambda t. And remember, the CDF of the Poisson distribution, so sorry, the PDF of the Poisson distribution, that was the e to the minus lambda times lambda to the k divided by the k factorial. Okay, now what is our parameters? The lambda t. So instead of lambda, I will put just lambda t, and that will be equal to e to the minus lambda t times lambda to k. The k is the number of success, and I know that there is no success event, there is no arrival. That's why the k will be 0, and the 0 factorial, the k factorial. That is 1, that is 1. So I will end up with e to the minus lambda t. So this guy is equal to e to the minus lambda t. That's why I will end up with 1 minus e to the minus lambda t. What is that? This is equivalent to the probability of x1 is less than or equal to t. Okay, so what is this? This is the CDF of exponential function, exponential distribution. Okay, if so, this is for the continuous case. If the case is discrete, the same interval, we have some discrete case, like we have some time buckets and the fail, and success, let's say, and we will stop the process here. Remember that we calculated this with the geometric distribution. Okay, so the second conclusion we just figure out is, if we are focused on the first success or first arrival, in other words, the inter-arrival approximation, if the case is continuous, we will use the exponential. If the case is discrete, we will use the geometry. Okay. Okay, now let's look at another problem, and we have the same time interval, and let's do this for the discrete case. We have some time buckets, and we have some failures, success, failures, success. So in the previous one, we just focus on the distribution about the first success, right? And now, let's say our interest is about the second, third, etc. success. So that was the first success, and this part is second success. And we just found that if the discrete cases, if we are considering the discrete case, we can do that, or we can say that that random variable is associated with the geometric distribution, or in other words, we can say that that random variable is said to have the geometric distribution. So this part, this first success, is have the geometric distribution with parameters p, right? And remember that the geometric distribution is the memoryless, so that's why the second part can be considered as a new experiment that will not be affected from the previous one. That's why this is also the geometric distribution with the parameters p, which is the probability of success. And this whole process, I mean, the second success is, remember that, the negative binomial distribution with the parameters q and p, which is the number of success interested. Okay, if that is the continuous case, and we have a success at this point and this point, we just seen that here, that is about the exponential distribution, the first success event or the first arrival, which is the exponential function, exponential distribution with the parameters lambda t, right? And this part, again, the exponential distribution is the memoryless. That's why the second one, the second part, second time interval is again about the exponential with the parameters lambda t, right? And if we consider the Q success, which has the Erlang distribution, okay? Erlang distribution with the alpha and the lambda, and in this case, the alpha is the number of successes in this case, which is 2. So this, if we consider the 2 successes, that has a the Erlang distribution with the parameters 2 and lambda. So we can generalize this one, the Erlang distribution with the parameters the k and the lambda, and the k is corresponds to number of success. So, and remember that if the k is 1, if the k1 is 1, that corresponds to or equal to exponential distribution with the parameters lambda t. And remember that if the k is 1, that is equal to exponential distribution, okay? So, and also remember that that is the special case of the gamma distribution, because in the gamma distribution, that alpha can take any real number, but if those are integers, we call that distribution as the Erlang distribution, okay? So in summary, what we learned so far, let's say the continuous and the discrete case, and that is one. The first thing, if we are interested with the total number of successes, for the case of continuous, for the continuous case, we can use the Poisson distribution. And for the discrete case, we can use the binomial, okay? If our interest is about the first success, the first arriving event, first arrival, in continuous case, we can use the exponential, and in discrete case, we can use the geometry. If our interest is about the second, third, etc. Success or the arrivals, for the continuous case, we can use the Erlang distribution. For the discrete case, we use the negative binomial distribution, okay? So, okay, in summary, we can conclude that there is some interrelationship between some distribution, and what we learned so far show that makes sense, okay? Now let's go back to the slides, and you can now easily understand the solution of this example. And we can say that the question was the consider a Poisson process with the mean lambda per unit time, and what is the distribution of the first occurrence time. Remember that this is the continuous case, okay? And remember that from here, the first one, the first success occurrence is about the exponential distribution, okay? We have already calculated this part. Okay, we have seen that the occurrence time of the first event is exponentially distributed in a Poisson process. The process itself is a Poisson, but the occurrence time of the first event is exponentially distributed. And for the process, let's say the process is arrival of the customer, just that is an example to make the concrete what we did so far. After the first customer arrives, the remaining process is also the Poisson process with the same rate, which is lambda. So the first arrival time of the remaining process is again an exponential random variable. And that is true for all the following arrivals, okay? We say that the inter-arrival times of the Poisson process are exponential with the parameter lambda, okay? The process itself, Poisson, and the inter-arrival time which means the first arrival, the second arrival, third arrivals, that inter-arrival times is exponential distributed with the parameter lambda. Remember that the mean and the variance of the gamma distribution are alpha times the mean and the variance of the exponential random variable with the rate lambda, with the parameter lambda. And this is not just a coincidence, because we just seen that if we, for example, if we consider the second arrival, that is equal to the Erlang distribution with the parameter 2. Okay, so so we can conclude that the mean and the variance will be the alpha times, and alpha corresponds to the k in our example. And when alpha is an integer, the arrival times of a Poisson process have Erlang distribution. We just seen that. And if we denote the xi as the inter-arrival time of a Poisson process with rate lambda, we have seen that xi are independent and identically distributed exponential with the parameter lambda. Okay. And the first arrival time, S1, which is equal to X1, is exponential with the parameters. And the following arrivals will be the Erlang with the parameters alpha 2 and lambda. For the third arrival time, the alpha will be 3 and lambda will be constant, and so forth. Okay, so we will do that will be the same for the following arrival times. So that concludes the 8th lecture, and thanks for watching. We will continue for the lecture 9.